Okay. Okay, let's get started. So, any question from last time? No. Okay. Where am I? Here. Yeah. So last time we go over these two protocols that are used in shared entanglement. They are superdense coding and teleportation. So in superdense coding, both of the protocols use Alice and Bob share entanglement, and in superdense coding, you are able to send two classical bits by just sending one quantum bit, because you can kind of encode your 2-bit in either the computational basis or the phase of this shared entangled pair. And yeah, and Bob is going to tell apart these 4 different build states. And in teleportation, Alice is able to send an unknown quantum state to Bob through a classical channel. And this is done by Alice doing some measurement on her part of this entangled state, and Bob's copy of this shared entangled state will become something that he doesn't know, but Alice will send the measurement outcome to Bob. Then when Bob gets the measurement outcome, then he knows what the post-measurement state is, and Bob can correct the post-measurement state into the unknown quantum state that Alice wants to send. The interesting thing is, so I think there are more interesting things here. The protocol is very delicate. It preserves all the information property of quantum mechanics. For example, concept here is unknown quantum state. So the quantum state can be unknown. That means that it has some coefficient. You know it's 1 qubit, but you don't really know the coefficient. And if you do a measurement, you will destroy it. So it's kind of a black box here that you need to carefully move around and not probing it. So this is so after sending the after teleporting this unknown state from Alice to Bob, Alice still doesn't know anything about this state, because so Alice gets some measurement outcome, but the measurement outcome just is a random number that's drawn from this 1/4 probability. So this measurement outcome doesn't reveal any information about your unknown quantum state. Your unknown quantum state is alpha 0 plus beta 1. But the measurement probability doesn't depend on this. And also Bob doesn't know the unknown quantum state, right? Bob knows he gets one of the 4 things, but yeah, the information Bob sees is also just a post-measurement outcome, which is a uniformly random number from 1 to 4. And Bob knows he should get a state, but he also doesn't know alpha and beta. So this unknownness of the quantum state is preserved throughout the whole protocol. And that's that's a theme in quantum information, where the unknown quantum state need to stay unknown, or you cannot learn anything about quantum state until you actually measure it. And there's no cloning, etc. Okay. So question about how teleportation is done, or what are we actually doing in teleportation. If not, then okay, let's finish this small bit of. Let me just check. Okay, we seem fine. Yeah, there's one bit of this chapter that is resource theory. So we can think this shared and entangled pair as some kind of resource, and because it is something that you cannot generate it locally. So resource theory usually means you have something free, and you want to study the limiting factor of all the operation you want to do on your system. And so, for example, in our two examples here, we have Alice and Bob, right? And we want to discuss the communication cost. So the first thing here we can do is what Alice do in her part, and what Bob do locally in his part. So so local operation are free in this resource theory. So things that like you pass classical information, pass quantum information, or have the shared randomness or shared entanglement, those are resources because they require communication to generate. And so we can think about this shared entanglement as a resource in this communication model. And so we define E bit, that means one maximally entangled state shared between Alice and Bob. And just once again, as a reminder, we think about shared entangled state as this thing, this EP pair, beta 00. Oh, we didn't say it here. It's here, okay? This beta 00, okay? And okay, well, here that's really nice. And from resource theory, then we can see that this beta 00 is the same resource as beta 01 and beta 10 and beta 11, because we say classical operation is free, okay? And this clearly you can convert between those four by doing local operation, okay? So Alice and Bob don't need to say anything to each other to convert between those four. Alice can just apply those things, right? Alice can apply Z or X on her part to change between those four. So they are same resource, but for simplicity, let's assume we are having some beta 00, okay? And then resource theory, so entanglement is one resource, then we can think about conversion between different resources. So for example, in superdense coding, we are thinking we are using one shared entangled state, one shared entangled pair, and using one qubit of quantum communication, then we can get something that let us send two classical bits. So, so in terms of resource theory, superdense coding is a protocol that converts one E bit and one qubit to two classical bits. Here, qubit and a bit means communication. And teleportation is kind of reverse, but not quite true, because it uses two classical bits. Remember, you need to send out 2 bits of measurement outcome, and 1 E bit to send 1 qubit of communication. And okay, so you see the 2 bit and 1 qubit kind of exchange with each other. So it's 2 bits here, 2 bits here, and 1 qubit, 1 BIP here. But well, it's not totally reversed because both of them consume one maximum entangled pair. So unfortunately, if you concatenate those two protocols together, what you get is you are just wasting your integral pair. So that's annoying, but resource theory don't always have conservation. So we need to design your protocols cleverly. Don't waste your resource too much. And finally, then we have another protocol. We didn't quite give a name, but this is how you create chain entanglement. That is, you can send 1 qubit to create one chain entanglement so we don't have a dedicated session for this, but remember when we start talking about all these things, we say we can get shared entanglement by having Alice create a shared entangled pair on her side locally, then send one of them to Bob. Yeah. So I guess this is all the quantum communication, this is all the quantum communication we scheduled to talk about in the class. Have any questions? If we have time, we might talk about QKD at the end of the semester. But yeah.
What's our meaning about free?
Free. Let's say. Just is a theory about how much resource you use, right? So free means you can use as many as you want, and you just don't count the cost. Yeah, it's kind of I don't know if it confuses you, but if you know complexity theory, it's like when you count the space complexity of your algorithm, then you can use as much time as you want. Yeah. So here, this resource theory is we are counting the communication resources, and so all the local operation is free. Yeah, you can do any. Yeah. Okay. Okay. If you don't have question, then we can go to next chapter. So wait. I should not open this. Sorry. We have 22 now. Okay. Yeah. So next chapter is density operator, and I guess I should have more motivation. So. Well, the motivation here is we want to describe a classical probability mixture of quantum state, and this very naturally come from, well, we're going to see a later part of the course. This naturally comes from when you want to describe a local part of an entangled state, or an easier example of just a probability mixture is here, this thing, right? So here in our, which one is this? Teleportation protocol, yeah. Yeah. In our teleportation protocol here, so at this point here, Bob can have one of the 4 states, right? Bob's state is 25% being this, 25% being this, 25% being this, and 25% being this. And well, that's just a really dumb way to describe his state. So one way to describe that is, well, you attach your probability and the state, probability and state, probability and state, probability and state. So that describes the thing Bob is holding. But so we are going to see soon in density matrix that there is a more elegant way to describe that you are actually holding this probability mixture of 1/4 of those 4 things. Okay, so yeah, so that's a small motivation. Sometimes you want to describe classical probability mixture of quantum states, because when we do some measurement, there are going to be some classical probability. Okay, and so here is a simpler example. So example, you do measurement on a plus state, so computational basis measurement on plus state, and it's going to be 50% probability being 0, 50% probability being 1. And what you are kind of trying to do is, okay, do we have okay, I don't have a good way to do this. But imagine you, okay, maybe this. So let's try if I can break out. Okay, yeah. So imagine if someone just break out this information, right? And yeah. So I think it's also like Alice and Bob. So Alice has this plus state and she do a measurement and will become those two things. Then Bob know Alice do this measurement, but Bob didn't know the measurement outcome. Then how does Bob describe the state Alice is holding? It's kind of this question. Okay. And okay, let's erase this and turn this back. And okay, yeah. So we want to describe this kind of thing in a simple expression. And so one thing that you might think is, well, this is like a superposition of 0 and 1, but it is not a superposition of 0 and 1. And so you cannot just write it as like, maybe I should write 1 over square root 2, right? Oh, sorry. There is no, sorry, this. Okay, yeah. This is not a superposition of 0 and 1 because anyone want to say why? That is on the example. Well, I guess a very obvious thing is if we normalize this correctly, then 1 over square root 2, it should be 1 over square root 2, 0 plus 1. But 1 over square root 2, 0 plus 1 is just a plus state. And obviously, if you do a computational basis measurement of a plus state, it will not stay as a plus state. For example, when you measure this ensemble in plus minus direction again, remember when we talk about the Stern-Gerlach experiment, when we measure this thing in the plus minus direction again, it's going to be 50%, 50%. But if you measure this in plus minus direction, then it's going to be 100% plus. So this probability mixture is is different from a superposition of 0 and 1. And that's something need to be careful. So there is classical mixture and there is quantum superposition. They are different concepts and they will be described differently mathematically. Okay, so let's back to our ensemble or classical mixture. So it's 50% 0 and 50% 1. So let's have a pseudo derivation of how should we actually describe this thing. So suppose our system, so very general, not that much general. Okay, so our system is in some quantum state psi 1 with probability p1 and some state psi 2 with probability b2. Obviously, p1 plus p2 should equal to 1. And well, then we think quite physically. So we think about the expectation value of some physical quantity. So remember, this is the second formulation of measurement. So assuming we are doing a measurement related to this Hermitian operator A, okay? And hopefully you also remember this. So the expectation value of A should be this should be, well, probability P1, the state is psi1, so then it's this inner product of A with psi1, and with probability P2, the expectation value of A is this thing. And then now we start to do weird things. Yeah. So first is we think this expectation value, well, it's a value, so it's just a number. But we think this number as the 1 by 1 matrix. So we can think this is a trace of this 1 by 1 matrix. So basically doing nothing. Okay, so this is a interesting mathematical trick. Then we are going to use this relation a lot. Remember, you can prove this somewhere. It's easy. That trace has this cyclic property. Trace AB equal to trace BA. That means trace of. So now where AB part is, this is A, this is B. So we can move this A to here. So this is equal to trace A psi1 bra, A psi1 Kate and the psi1 bra. Okay, and we do the same thing here. So it's A, this is B, and we move this here. Okay. Now this trace is actually doing something because this is a matrix, right? This is matrix A. Then this is row vector. This is column vector, and this is row vector. Okay. So this is a nice trick to know. You can do this kind of operation. It's true. Okay. So this is a matrix. This is a matrix. And finally, we know that this trace is linear, and we can move things around. So you can move this P1 inside, P2 inside, and doing the addition together, and you get this trace A and P1. That is projector on side 1, and P2 times this projector on side 2. And okay, so this part doesn't depend on A. So A is here, right? And so you see this expression has really nice separation. So this is A, this is the thing you want to measure, and these are all things that depend on your example. There is P1 and psi 1 and P2 and psi 2. They are all in this expression, and it is a matrix. Okay, because the projector is a matrix, projector is a matrix. Matrix has a number is still matrix, matrix has a number is still matrix, matrix plus matrix is still matrix. And yeah, so here is your density matrix. Our derivation shows that the expectation value of any operator A is determined by this P1 times psi1 projector plus P2 times psi2 projector matrix. And we'll generalize. So this is not a derivation yet, but we basically make a definition now. So you have any ensemble of quantum state, so some probability and associated quantum states, so some pi and psi. And then we can define the density matrix to be just, well, basically the weighted average of the projectors. Okay, so it's some I pi, then projection I. So yeah. So here we just define this correspondence for every ensemble. Obviously, you can calculate this density matrix. But okay, so spoiler, this is not one-to-one. So there is a function from this set to this thing, right? Obviously, you can just do this calculation, but there are different ensembles that give you the same density matrix. Yeah, but that's something we'll talk about much maybe today. Anyway, that's something later. And okay, so the upper part is just a definition. Now we are actually stating a theorem part. Okay, so the theorem part is, so every physical property of the ensemble is actually just described by this not one-to-one matrix called density matrix. Okay, so this row will describe everything about the system. Okay, and here So we keep talking about this name ensemble, and this is a more physics term. And what do we mean by ensemble? Is just a probability mixture of things. So classical probability mixture of something. And here we are talking about probability mixture of quantum states. Okay? And yeah, so there are a whole bunch of quantum states, and we think each one of them is drawn with some probability. Okay? So that's just what the ensemble means. For example, this is the ensemble of 50% being 0 and 50% being 1. Okay. And okay, so this is kind of a theorem part, and we need to prove it. So we need to prove that this law describes everything about our ensemble of quantum states. And if you count the axiom of the if you count the axioms of the quantum mechanics, then there are two other things to check. So here we are basically replacing states with this density matrix. Then we need to say how it evolved and how it how it responds to measurements. Okay, and so for evolution, remember for usual or so what we had before is you have a quantum state, and it will evolve correspond to some unitary. It can be any unitary. Okay. So, or more like you apply something to your system, then every state will evolve through this law. Right. So I should say this U is kind of like a gate. And if you apply this gate, then every input state is going to map to an output state that is U times psi. Every input state psi is going to be mapped to the output state U times psi. And okay, so now back to our example. And so your input state is drawn with some probability pi and it being psi. Then we say every psi mapped to U psi, so psi should be mapped to U psi. So, so here we will go back and forth between this ensemble interpretation and our density matrix. Not quite back and forth. We'll see how you do to the ensemble first. Okay, so you have this ensemble, and ensemble evolve to this ensemble, and then the post-evolution ensemble has density matrix where we just write down the corresponding formula, right? So some I pi and U psi I kate and U psi bra of U psi, which is the complex conjugate of U psi I. So psi kate becomes psi bra, and remember you do complex conjugate, you should become U dagger. Okay, and so it's this thing. Now you do linearity, so you grouping together everything that depends on I. So you have this summation here and this pi. But remember pi is a number, so you can put it anywhere. The ordering doesn't matter, so you can put pi here. And this matrix multiplication is linear, so you can also pull the summation inside. And give it. So those are all the things that depend on I. Okay. So there's some I, pi, psi, psi, and you look at this, then you will realize this is a density matrix correspond to the original ensemble. Okay, and yeah, so your post-evolution density matrix is just U times rho then times U dagger. Okay, So we derive that you can. So here we show that you can describe the post-measurement density matrix that corresponds to a post-measurement ensemble by just writing U row U dagger. So you don't need to write down things in the ensemble ensemble interpretation. You can just describe this thing with U times rho times U dagger. Okay. Don't need to look at the PI to write down this. Okay, question? Not. Okay, then let's check measurement. Measurement is more complicated. So I want to see what are the measurement probabilities and how do you write down a post-measurement state. And hopefully it can also be described by rho in some mathematical expression. So, well, there's measurement. So let's suppose we do some measurement. So the most generalized measurement, describing by the set of m, big M sub small m, and also on your ensemble of pi and psi I. And okay, then the first thing you want to know is what is the probability of getting outcome small m. And well, then let's just do calculation. Okay, so the calculation, we need to be a little careful about our probability here. We have a whole bunch of conditional probability. Okay, so first we calculate if your input state is actually you draw psi I, then what's the probability of getting m? Then then this is a formula we have in chapter, in I guess previous chapter. Anyway, in our postulate, we have this formula which is basically a known square of n sub n apply psi, and then we want to write things in matrices, so we do this cyclic thing again. Okay, so remember this trace AB equal to trace BA. So we think these are the trace. This is a number. We think this is a trace of the number. Then we trace A and B equal to trace B and A. Okay, so we do the trace trick again, and get this formula. And now you see we are trying to group these projector on psi together. Okay, so this is a conditional probability of if your input state is I, and you get the measurement outcome M. Now we need to do probability theory manipulation of what's the total probability of getting M. Well, then that's all the conditional probabilities summing together, right? Because PM condition on I times PI, the two together is probability P and M. Okay, and obviously probability of M is all the joint probability summing over I. Okay, so that's probability theory, and then we need to write down numbers. Okay, so we calculate this here, and you write it down, and then then once again we use linearity. Then we pull this thing inside here, and you see that once again, and that's everything that depends on I. And once again, you see this sun I pi project onto psi. That's rho. Okay, so it's a trace of this part that depends on your measurement operator and your input density matrix here. So you can see the post measurement. So measurement outcome probability can be described by this density matrix rho in a nice expression. Okay. Okay. Let's erase all these H1 lines. Okay. So the outcome probability is checked. Then there is post measurement state. Then this is more annoying. So once again, we condition different states I first. Okay. So suppose your state is psi, then after you getting outcome m, the state will become this m sub m psi I, will end with some normalization. Okay. And here we write this a little differently, because we look at this thing here and we remember this is the square root of the outcome probability here. Okay, they are the same expression. Hopefully you remember this. And anyway, they are the same expression, so you can write this as square root p of m condition I. Okay. Then okay, so this is a post measurement state if the input is I, and then the total state or the total density matrix of the outcome ensemble is okay. So I should add one more line here. Okay. So we can think about the outcome ensemble. It is so we have an outcome ensemble that's well, basically the ensemble corresponding to this, right? Let's see. Probability I condition m. So because every input state will corresponding to different post measurement state, and they are the thing we write here. So psi mi, and their probability is going to be some conditional probability. That's just pi condition outcome is m. Probability of input is I, condition outcome is m. Okay. And okay, so your starting ensemble of this thing will become this thing, given you know the outcome is m. Okay. And then once again we use the ensemble interpretation and we write down the. So we think the ensemble becomes this thing, and so this is a little circular logic, but should be fine. Then, so we think the corresponding density matrix is you write down this sum over all the probability and the projectors. Okay. Then once again we need to deal with this probability. So what's actually this pi condition on m? Then pi condition on m, well, by definition of conditional probability is pi and m divided by pm, and you swap this around. So what we actually know is pm condition I, and so pim is pm condition I times pi. So this is quite standard probability manipulation. So this thing equal to, so this pim is this part. So pi here, then PMI, and PM. And then we have this projector onto psi n sub I, and we have psi n sub I here, and then we can run our projector here. So this thing squares, so you get rid of square root. The upper part becomes this thing, right? Then we do the cancellation that we really want. We cancel this P and condition on I. Okay. Now what do we get? And yeah, so now only thing dependent on I is the summation I, Pi, and project onto side. Very happy. So once again, everything is linear, and you group everything dependent on I. And you found out that that's rho. Perfect. Okay. And okay. But this is not quite finished because we cheat a little bit. So there's this P of M here. And I don't think we calculate P of M anywhere yet. But wait, sorry. Sorry. I'm stupid. So yeah, we calculate P of N, yeah. So P of N we calculated here, right? So I got a little stuck. Yeah, P of N is the probability of outcome N. So here is also described by this rho. So it's this trace. Oh, what happened? Okay. Yeah. So P of N is this trace M dagger M rho, and well, but we upper part we have this M rho N. So once again we cyclic this trace a little bit to make it nicer. So it's trace M rho N and dividing M rho N dagger. Okay. So that's a post measurement state, and so that's quite complicated formula, and you probably want to memorize this later. But for now, we finished our derivation. So we show that this thing is also described by rho, meaning that you don't need to go into this Pi and the psi detail to write down this rho n. Any question? Okay. Here you can see this symmetric thing, so it's M rho M dagger and dividing by trace of it. Okay, and okay, we got some more time, so we can talk about this. So notations. So now we have density matrix. Then we need to distinguish things that are density matrix and not density matrix. So so if a density matrix can be written as a projector on some state psi, then we call it a pure state. Okay, and a pure state is just basically a state we have been having. So like all throughout this, those are pure states. Because we can think of pure state as an example of being 100% just one state, right? So yeah, so just a notation thing. So this Kate, so this vector, this Kate state we have been using is called a pure state, and this thing can also be seen as an example and has this density matrix corresponding to it. It's a rank 1 matrix, and this matrix is also called a pure state. So yeah, so a matrix can be called pure state, a vector can be called pure state. They're basically the same thing. And so there are things that can be written in this way, then there are also things that cannot be written this way, and those are called a mixed state. Okay. And so to be more complete, so we talk about probability mixture of pure state, then become a mixed state. So what if we have a probability mixture of mixed state? Well, it turns out this is quite, I think the mathematical term is complete. So if you have probability mixture of mixed state, it's still mixed state. Basically because if a probability mixture of probability is still probability. So here we have a short derivation. So if you have an ensemble of some density matrix rho I, and each rho I is an ensemble with some Pij and Psij. Actually, yeah. Okay. So with another index j. Okay. Then the total density matrix. Okay. So we are also giving one step here. Then this whole thing can be single as an ensemble that has, well, they have states, those Psij, right? And each Psij will have probability just chain rule together, so Pi times Pij, right? And so here you can see these Pij are actually more like Pj condition I. And anyway, so these two things together correspond to this ensemble. Oh, why is it so slow? Then we can write down the density matrix. It's this thing. It's some ij, pi, pij, Psij, Psij. So this obviously is a mixed state, and but we can go a little further, and so we can group things together. So everything that depends on j. So this depends on j, this depends on j, and we put some j here. And you see this is rho I, and so you see that what we derive here is probability mixture of mixed state can be described by this is also a mixed state, and it can be calculated easily through this formula. You just average your density matrix together. Okay. So here we have more complicated example of density matrix. So very general case of this thing. And it's a density matrix after. Okay, so it's an example of this thing. So if you measure a density matrix rho with some measurements n, but you cover up the outcome. Okay, so if you measure a density matrix with measurement, and you know some outcome m happen, then the post measurement state is this thing we derive. But if you cover up the outcome, so you do a measurement that changes something, but you don't know which outcome it actually happened, and then you think of that as a probability mixture, then the corresponding density matrix will be sum over all outcome probability. So this thing we have here, right? So sum over all outcome probability times all the post measurement state. Okay. So okay. And well, the outcome probability and the post measurement state we had before. Outcome probability is here, and the post measurement state is here. And then you write them out, and you find this summation m, and those measurement operators which in your density matrix. So there's a really clean formula here. Okay. And then let's see. Oh, it's time for a break. So let's take a break now. Oh. Any question? No question. Okay. Oh, also you can turn your homework here.对啊。
刚刚那个讲那个EB 车跟 EB 的这个地方，因为 Result Theory 它在那个课本有吗？因为我
Result Theory 好像有吧，有一点点吧，没有吗？我记得有吧。
在课本找看
哦，可能没有，我不太记得。
有些是我还读说对 EB 它的 E 到底是什么？
就是他们有先 share 了这个 entanglement 嘛，
所以可能例如说我
有点像 share 那词的感觉。如果你知道子宫的，
所以可能例如说我有一个什么 EPR state，他们两个东西就是一个 B 的 share 两个，
对，
这就是一个 EB 的。
对。
那下面的等式是怎么成立的？
这其实不是等式，这是 convert， 是说我用了这两个东西，然后我拿到这个东西。
就是我拿到这两个要素的话，可以
做这件事，这个东西可以做的事情。对。
然后我拿到两个 bit 加一个 EB 可以得到一个 2 bit 做的事情。
对。
那这样子列出来是讲说什么哪一个方法的效果最好，还是？
只是说就是说这些事情你可以做到这样子。跟大家说，然后你就可以去组合说有什么其他的事情也可以做到之类的。对啊。
这样子。
但是这两个组合起来就不是太有用啊，就是两个组合起来你就发现有东西消一消，然后就发现只有两个1bit，然后变成什么都没有。对，
好，谢谢。
所以 OK。
刚刚那个什么 example 那边，就
example 吗？
那个是唯一可以写成那个形式。
什么意思？哦，不是唯一啊。等一下，你要说的是什么？是我在说的那个吗？你是说不同的 example 有可能会变成同一个 density matrix 的事情吗？这个不是唯一的。这我们今天应该就会讲到。就 density matrix 就是一个 matrix 嘛，反正就是一个矩阵里面有一些数字，对吧？然后 example 是一堆
projector 加起来。
对啊，一堆 projector 加起来。例如说，我马上就看到，我这个讲的太理论了。但是，例如这样子就是一个 density matrix 嘛。
刚刚那个有说 pure state 跟mixed，就是说可以写成。
如果只有一个state 写出来的 example 的话，
但也有可能它是可以写成其他的。
如果只有一个的话，那这个就是唯一的。虽然说我们可能不会，
就我们可能只会知道这个矩阵，然后
我知道这个矩阵，但矩阵它写成这样，可不可以写成这样子是你可以算的啊。你矩阵的话，可以写成这样的话，rank 一定是1嘛。就是你就去把它diagonalize。我们之后会再讲蛮多，但是就是如果要是 density matrix 的话，一定要是可以diagonalize的东西。对，然后。它可以diagonalize，然后你diagonalize之后，因为它是这个东西嘛，它是 projector 嘛，projector 到一个 state 上面，所以基本上它会有一个 eigenvalue 是1，然后其他 eigenvalue 全部都是0。对，然后这个是1的东西呢，就是这个 state， 那个1对应到的 eigenvector 就会是这个 state。
那后面有讲到 mixed state 那个组合在一起还是 mixed state。它不会就变，有没有可能变 pure state？
不可能吧？你用刚才那个，我想想看，我觉得不可能，我记得是不可能。等一下要知道怎么证明。
消掉，然后什么就。
因为它是加的，它不会消。
里面的数字都是这样。
要怎么证？我有点忘记了。因为 probability 只有正的东西，所以它不可能会消掉。
不知道 projector 矩阵里面会不会有负的？
不会 projector 的 eigenvalue 只有0跟1啊。
但是它矩阵的话有可能。
对，矩阵的 element 会消掉，所以我在想这个证明是怎么证的。物理系有证过。
但是这个结论是正确的，就
mixed state
example 在一起会是会是
会是 mixed state。我在想要怎么证明这件事情，突然这样想，我忘记了。
我还想问之前。
好，我们先弄其他的，先不要纠结这个。是你问我那个 global face 的问题吗？哦，不是，好，没关系，继续。predictive measurement， 啊。对，就是 completely。
然后为什么这个可以推到 EITJ？
我想的是，
回去自己在站的时候，
怎么说吧？
这个 EJ，然后这，那你可能可以把I等于这个，我只能写出这个。
我觉得我是想的是 eigenvector， 就是，我想的事情是他们会 ，OK， 这个不是证明，但是我想的是 identity 是这样子一堆东西嘛，然后那些 projector 也有，就是 identity 是一堆这样子，然后我说加起来意义是他们也要把它们分坏这样子，可能这里是一个 projector， 这里是一个 projector， 然后这里是另外一个 projector。
我在想他们的 eigenvector
但是
不一样。
如果说他们没有垂直，是不是？但是我觉得还是不太可能。加起来的一，你说，所以我们现在要的反例是怎样？是，好，我们就只有两个好了，两个，如果两个跟很多个应该是一样，两个对。好，所以然后加起来的人，我记得我的手机有人打给我，谁？感觉是广告。喂，你好啊。那个应该不是 projector， 这个也不是 projector， 真的没有必要，好，谢谢，我在工作哈。
那这个第一道的，这样子
这个是 projector 吗？这应该不是吧？这个连带跟来这波都不是。
所以它符合之后就是。
OK， 我应该要说，projector 要带跟来这波，这个不行。
可是只要 P 平方等于 P 就是。
OK， 应该是要再加的，应该要带跟来这波。这个不带跟来这波。这个是。
我以为是会长得像这种样子，
但是这个显然不是这个东西嘛？你有把这个显示这个吗？应该不行吧？你要找什么塞可以是要这样子。
所以 projector 这边指的是可以写成这种形式。
对啊，要上，应该说要可以 U， 然后我也不知道该怎么，E 吗？ E 加 U， 应该说 eigenvalue 都是0跟1啊，这样。也要 UDU， 然后这个 D 也要是1，
但是符合这个好像是可以推论出 eigenvalue 是。
对啊，可是你要带过来这个嘛，就是你这给我你说它符合这个，但是它eigenvalue 不是1跟1，你约目前不知道在哪里。因为它负载跟来这个东西嘛。对，但你那个怎么证？我现在我想一下，如果你想要听的话，我可以下课后我再来试，应该这样说。用 eigenvalue 来分析它。
需要这个等于0，就是因为。
就是你不希望那个 eigenvalue 重叠的感觉吧？就是没有的话，说不定有一个 project 在这里，有一个 project 在这里，那加起来，所以2你就爆了。对，你希望是分开来的。
这个之后是要拿来算那个什么 state 的，那个什么 state。
对啊，我觉得应该是快到水上面。
那会。
对啊，这个就是要算说 post measurement state， 就是你有一个 side post measurement 变成 pi side 之后，然后后面会说，然后再乘 pj 的话就等于0这样，就是 projective measurement， 你希望那个 result 是结果是，所以可以用这个就差不多整完，就是我说的那个结果不会变啊。就有点像是我们那个 Stanger， 就是我们的那个例子这样子，然后我们用立方这样量，它变0跟1嘛，就是 project， 然后0的东西你再去分的话，就只会是0了，就是这个没有这样子，就这个先后来式的事情，就是说你量到0之后，你再去量一次0、1的事情，它就不会跟你讲是1了。对，这样子。Okay, any question that you still want to ask? If not, okay, let's continue our density matrix. So, wait, pen? Yeah. Where were we? Okay, so finally we can see this algebraic example. So an easy example of the density matrix, and also the starting example. And last you have your plus state, and you do computational basis measurement of 0 and 1. And now let's have the density matrix. And okay, so you start with this density matrix that is a projector onto plus, and you can calculate it out. That's 1/2 everywhere. So it's a density matrix of the starting state. Then you do measurement, this measurement, and then you apply this formula here. Okay, so your measurement operator is either this projector on 0 or this projector on 1. Oh, I'm missing the thing. Okay, let's use red. Okay, this projector on 1. And so the post measurement state, so let's just put in the formula. Then it's rho and sandwiched by m, and rho sandwiched by another m. Okay? And and so here we do some calculation, and you see this is a number, this is a number, and this is number obviously 1 square root 2. Hopefully you can do the calculation, and so you get this 0 cat times 1/2 0 broad, and the same thing here, this is a number, this is a number, and they multiply together to 1/2. So yeah, it's the same thing here. Then I'm missing another line here, and yeah, so you group things together to the linearity. So things C is 1/2 times the identity, and then you write down the matrix. Then it's this matrix, 1/2 and 1/2. Yeah. So this is our first example of a density matrix. Write down its number, and it is quite famous density matrix. Hopefully you can see it here because you see it's beautiful. It's very symmetric. 1/2, 1/2 here. Diagonalized everything, and also it's proportional identity matrix, and it's very nice. So it's called a totally mixed state because, well, it's it's more nice. It's also it's called totally mixed state or maximally mixed state. Okay. So maximally mixed state. And you can kind of see the maximum here, because if you want to deviate mostly from being one state, which is probability 1 and 0, then here the max you can get away is 1 over 2, 1 over 2. Well, yeah. There are a little more about this. Not sure we will cover, but yeah. And so this is a totally mixed state or maximally mixed state for 1 qubit. And depending on your view, this thing has no information or most information because it's maximum entropy. Okay. So that's totally mixed state. And I guess we can have, let's have this homework. I'm not sure. I don't think we have, right? So we have homework. That is, you can try to calculate the density matrix of this thing. Okay. So density matrix of teleportation. And I will just tell you. Is a totally mixed state of 2 qubit, but you need to show the calculation. Okay, so that's something interesting you can do in your homework. Okay, and okay, now we come with the elegant and the simple theorem about density matrix. So we have been saying a density matrix. Well, density matrix correspond to some ensemble described by probability and pure states, and the corresponding density matrix is this thing. Okay. And but this is more natural than probability and the pure state, because if you just draw any matrix row and it satisfies those two conditions, so trace row equal to 1 and the row being PSD, so if and only if this happens, then it's a valid density matrix. Means that there is some probability distribution, means that it corresponds to some ensemble with Pi and Psi. Okay? So maybe let's read this theorem once again, line by line. So an operator row, so any matrix row, is a very density matrix, i.e. it is the sum I projected on Psi for some ensemble Pi and Psi. So it's valid, meaning it's correspond to some ensemble interpretation, if and only if row satisfies these two conditions, trace row equal to 1 and the row being PSD. And trace row equal to 1 basically means it's same as a vector being unilength. Okay? So this basically means the probability equal to 1. And so something, I'm not sure we write anywhere. So here intuition we have is that the trace of density matrix basically correspond to probability. You can kind of see it here, right? So your post-measurement density matrix is here, and then you normalize by its trace, because its probability is its probability. Similar to what we do on states. Anyway, let's go through the proof. So this is an if and only if statement, and there are two directions to prove for this kind of statement. So first direction we do, I think this is the easy direction. We go the only if direction. That means you have an ensemble and you write down the corresponding density matrix and you want to check those two conditions are met. So yeah, let's check. That's straight up calculation. So trace row of this thing, so trace of this thing. then everything linear, you can put trace inside. And once again, we use our favorite cyclic identity of trace. So you put the side, or you put this side back here. So you trace a number. Now every side is a unit vector. So this inner product is just 1, and trace 1 equal to 1. So this is just summation or pi. And yeah, it's an example. The probability should sound equal to 1. So this is 1. That's required. Question? And okay. And then another thing we should check. We want to check rho is positively semi-definite. And here the definition we use is that if you sandwich rho with any state psi, it should be greater or equal to 0. And yeah, then you sandwich rho with any state psi. And you write down your rho equal to this thing. And linearity, you pull all the summation I. And you pull this out. And now you have psi inner product with psi and psi inner product with psi. And that just, so remember this is a complex conjugate of this thing. So this is just psi and psi inner product absolute value squared. And well, so this is the probability. This is greater or equal to 0. And this absolute value squared. This is also greater or equal to 0. So you sum over a whole bunch of greater or equal to 0 thing, and it's greater or equal to 0. Okay. So yeah, so we check condition 1 correct, condition 2 correct. So the first direction is finished. Then let's check the second direction. So trace rho equal to 1. So this is okay, the harder direction. So you have any density matrix with trace rho equal to 1 and rho equal to PSD. Then we want to write it as this form for some ensemble pi and state psi. Okay. And this is not unique, but we'll find one of them. And okay, let's talk about strategy. So strategy here is we basically want to diagonalize. We want to diagonalize 0. Okay. And then it will be very natural to find the probability and the states, because it's going to be like the eigen decomposition. But okay, there's a trouble. So the first thing we need to show is rho actually diagonalizable. Okay. So we need to prove this lemma here. Let's kind of separate it. So lemma is this part. Okay. The lemma, okay, it's not quite showing it's diagonalizable because we are showing something stronger. So we show that if rho is PSD, as defined here, then rho is a Hermitian matrix. And we do this by decomposing rho into its real part and imaginary part. And so the real part is rho plus its complex conjugate not quantitative complex conjugate because we are saying matrix. So rho plus the conjugate transpose, so rho plus rho dagger, and average together. And B is defined by this rho minus rho dagger, and over 2 times minus I. Okay. And well, then you can check that A plus IB equal to rho because that's how we set up. We want the A and the B that are both Hermitian matrix and less on, and A is like the real part of rho and IB is like the imaginary part of rho. So A plus IB, then if you multiply B by I, then this I disappear. Then yeah, then the minus plus minus rho dagger cancel, and the rho plus rho equal to rho divided by rho plus rho divided by 2 equal to rho. Okay. So you can check this is true, and also by how it's set up, A dagger equal to A. Well, obviously if you dagger this thing, then you just swap rho dagger and rho. That's correct. And when you do dagger on B, then this number here, this minus I become plus I, and you swap the rho and rho dagger here, you got the minus I, but I'll cancel the minus I you get on this I, so it's still B. Okay. So that's a nice trick. You can decompose any rho into this real part and imaginary part, and now we can do our PSD thing. So PSD says that you sandwich rho with any psi. This should be greater or equal to 0. Okay. Now you have this decomposition that you put in, and you have a Hermitian matrix sandwiched by 2 things, and it is real, and another Hermitian matrix sandwiched by a state. This is real, but you have another I here, so this part is actually imaginary. But we want rho sandwiched by things being greater or equal to 0, means that this, when we write things greater or equal to 0, it actually means it's a real number. Real number don't have imaginary part. So that means yeah, that means that for all psi, B gets sandwiched by psi should equal to 0. Okay? And now we are very picky here. So B is Hermitian, means B is diagonalizable. Right? So I should write it here. So B satisfies this, and also B Hermitian, so B diagonalizable. And so we can pick those psi as eigenvectors of B. then this means that all the eigenvalues of B equal to 0, right? Because if psi is the eigenvector, then this calculation is just the corresponding eigenvalue. So all the eigenvalues of B equal to 0 means B is just 0. Okay. And well, B equal to this thing, and you can do a little manipulation, and that means rho minus rho dagger equal to 0, and rho equal to rho dagger. Okay. So that's a very careful calculation to show that rho is PSD, then rho is Hermitian. Okay, and finally we get what we want. Rho is Hermitian, and as in the first few class, which we claimed that rho is Hermitian, rho is diagonalizable. Rho is diagonalizable, so we can write it in this form. sum over all eigenvalue and the projector onto the eigenvectors. Okay. And also it's Hermitian, so all those lambda I are real number. Okay. And finally, we can now use, no, not quite. Well, we finish using our Robin PSD. Yeah. And I guess finally we are going to use this greater or equal to 0. Now, just like how we deal with B, we choose those psi as those eigenvectors of rho. Okay? So we sandwich rho with its eigenvectors, and now you can see the calculation here. So you sandwich this thing, then this psi times psi equal to 1. Psi times psi equal to 1, you left with lambda I here. So this just means that lambda I is greater or equal to 0 for y. Okay? So here we also prove that. So on here, basically we prove that the PSD matrix is diagonalizable and its eigenvalue are all greater or equal to 0. I think I said this casually many times everywhere, but now we have a rigorous proof. The PSD matrix is diagonalizable and its eigenvalues are all greater or equal to 0. It's nice to know. And okay, now we use this expression more, and we finally use our condition 1. Now what does this trace rho equal to 1 mean? Well, now we calculate this trace. And we skip a lot of steps. Hopefully you are already familiar with this. You move this trace here and see the trace projector equal to 1. So this is just summation of lambda I. So it means sum over all lambda I equal to 1. So we characterize a lot about these eigenvalues of rho. They are non-negative and they sum equal to 1. And that are just conditions for probabilities. So those lambda i's are actually probabilities. And yeah, so we are finished. So rho correspond to, I guess so this is a little annoying, it's not quite equal. So maybe I should write the arrow. Rho is representing this ensemble of probability being lambda I of getting the vector, the states that are the eigenvectors of rho. Okay. So this is one of the ensemble rho is representing. Okay. Question about this theorem. This is a really nice theorem. It tells you that totally get rid of the ensemble interpretation of rho. You can just write down matrix, then check this is true, this is true. Then it's a very quantum state or very mixed quantum state. Okay. And there are, so once again spoiler, there are many ensembles giving same density matrix, but if you want to find one of them, then you diagonalize it. Okay. Okay. Yeah, so let's unify everything together. So we know that rows are, what kind of rows are valid and how rho evolve upon unitary, and how rho respond to measurement. So we can describe so we can totally get rid of the ensemble, as I said, and we write down those new set of postulate of quantum mechanics in terms of those density matrices. So this will be more general than pure state, obviously, but as you might probably already feel, this is more annoying to say because there are more things to write down. So while this is more powerful, we don't always use this. Actually, we'll almost never use this on the later part of the course, but this is for completeness because it's an integral part of describing quantum mechanics. But when we describe algorithm, we'll use pure state because they are easier to write. But anyway, let's see those postulates. Physical system has a Hilbert space. So Hilbert space is okay. No, it's a little weird. So this is still a linear space with inner product, a complex linear space with the inner product. And anyway, so a physical system has a Hilbert space, and a dimension larger basically means your system can hold more information. And now the state of the system is described by these density operators. Okay? And the operator has same dimension. It's a matrix, and it has same dimension as the Hilbert space, and it's called the operator because we think it is think this matrix as a linear transformation from this Hilbert space back to itself. This is some mathematical thing. And anyway, this operator, now this is very important. This operator needs to satisfy these two things that we prove. So every density matrix needs to satisfy trace row equal to 1, and row being PSD. This is how we write row being PSD as a shorthand. Row greater or equal to 0. Okay. And hopefully you already see that this can already get a feel that this trace row equal to 1 is happening because you want the probability to be 1, the total probability to be 1. So as compared to pure state, we have that so for this condition we have that the psi is a unit vector, right? So norm of psi equal to 1. And the second postulate, okay, and if the system is evolved, is a closed system, then the evolution is described by a unitary matrix U. So if it's an open system, then actually there are also generalization here, but we won't quite touch it. Okay, but actually we already see. Okay, if we have time today, I will talk about this. But for now, let's say we have a closed system, and then the system will evolve under some unitary U. And we see that you apply a unitary U to rho, then rho becomes this rho prime, that's U rho. Why do I say U prime? It should be U dagger. Okay, so many typo here. Okay. And yeah, open system can do something else. And I guess, yeah. And postulate 3, when you do measurement. So measurement are still described by this measurement operator, whole bunch of operator n sub m, and they need to satisfy completeness relationship, sum over small m, m dagger m equal to identity matrix. And so you measure a state row with those operators, then there are two things. Then there is the probability of measurement outcome M equal to trace. I should write it as a more symmetric form, right? So it's a trace of M row M dagger. It should be small m. Right? And the post measurement state is M row M dagger divided by this probability, which is M row M dagger divided by trace of M row M dagger. Okay, so here you can also see kind of the subnormalized state thing, right? You can just think the post measurement state is an M row M dagger, and then there is a probability associated with it is a trace of this state. So you can kind of feel that the trace of a density matrix is this probability, and if you want to normalize this density matrix, you divide it by its trace, then you get back to this trace 1. Okay. Then we have the similar thing when we talk about subnormalized pure state. We say the post-measurement state is kind of this thing. Then you can see the probability here, and then you can normalize it to get the actual post-measurement state. And here we have the post-measurement state being M row M dagger. So it's similar to this thing, right? So whenever you do anything to a density operator, you need to sandwich it with something and something dagger. And yeah, and now we have the post-measurement state of everything. That means not knowing. So this basically means not knowing outcome. If you do a measurement and you don't know the outcome, then the post-measurement state will be, well, the weighted sum of this thing, and it's actually a simpler term. So rho sum m and m sub n, m sub m dagger. Okay. It's actually a really nice expression. And okay, and to confuse you a little bit, so this is actually, we say, if you have a closed system, you only do this thing, right? You only sandwich your row with some unitary u. And so this is actually an example of an open system. Okay. So hopefully this doesn't confuse you too much. But remember, we have, where do I find? Probably here, right? Wait, it's actually here, right? In this, we talk about generalized measurement can be seen as your system, and there is another system, and you do a unitary, then you measure another system, right? So this is the open system. Open system means your system is interacting with other things. Okay. So yeah, open system, your density matrix can evolve to things like this, and but it's also out of scope of this course. So let's just leave you open-ended here. And if you want to look up how this thing actually works, it's called quantum channels, and you can look up Nielsen and Tron. I think it's on chapter 7 or something. Yeah, it has an interesting series. Okay, so let's go back to our postulate, and yeah, we also have our postulate of composite system. And so for composite system, then your joint density matrix is tensor product of everything. Rho 1, tensor rho 2, tensor rho 1. And they are really, this is a really large matrix. Yeah. And entanglement here is actually quite complicated. The entanglement theory for mixed state is much more complicated, but let's just say we won't go into too much detail. So let's just say entangled state are just state that don't totally equal to rho 1 tensor rho 2 tensor rho 1. Yeah. But there are more things to this. We won't go into detail. So question about the postulates. This basically summarizes everything we talked about. The density matrices. And so the formula here, you want to memorize them. Okay. So these two conditions, really important. Please remember trace rho equal to 1, rho being positive, semi-definite. And well, it's going to be in your homework and in your test. And after evolution, rho become u rho u dagger. And after measurement, rho become m rho m dagger. And so the probability is trace m rho m dagger. And the normalized state is m rho m dagger divided by this trace. And then there is this. If you don't look at the measurement outcome, your post-measurement state is some m rho m dagger. Okay. So important to remember. And then okay. Then there's this part we don't have time to prove over, and actually don't want to prove it. I think I can leave this as a reading. But let's go over this thing. Wait, let me see what's the other part. Okay, that can be next week. Yeah, then let's finish this. We have enough time. So there important concept or important fact of equivalence of different examples. Yeah, we talk about this here and there for a while, that there are different examples that will give you the same density matrix. So for example, our favorite totally mixed state, it can be written as many different examples. For example, well, it's kind of easy to see because this is a degenerate matrix, right? So remember, it's 1 over 2 times the identity matrix, and the identity matrix can be rotated in any direction, and you have 2 eigenvectors. So this is kind of what happened. So because any 2 vectors that are orthogonal can be think of as eigenvectors of identity matrix. And yeah, so for example, this totally mixed state can be think of the example of 1 over probability 1 over 2 being 0, or probability 1 over 2 being 1. And here you can see the calculation check out. So you have 1 over 2 times this projector onto 0, plus 1 over 2 times the projector onto 1, and this is 1 over 2, 1 over 2. And also you can decompose this 1 over 2, 1 over 2 into plus minus direction. Okay, and let's do the brute force check. So 1 over 2 times projector onto plus, which will be this 1 over 2, 1 over 2, 1 over 2, 1 over 2. And 1 over 2 times the projector onto minus. Then 1 minus is 1 minus 1, then you get a minus sign here on the off diagonal. Then it cleanly cancel out the off diagonal elements, and you get back to this 1/2, 1/2. Okay. So yeah, these two things give you the same density matrix, and I'm not sure how you feel, but I think you should feel this some kind of surprising because, well, if you look at the ensemble, those two ensemble looks very different, right? This is in the 0, 1 direction, and those are two states in the plus minus direction. But they give the same density matrix, and remember here, the postulate, we keep saying that the density matrix tells you everything about the system because whatever you do is just described by the density matrix. So those two ensembles give you the same density matrix. So they are the same state. You cannot distinguish those two things in any way. They are just the same thing. Okay, so that's kind of surprising. They look very different in terms of ensemble, but the same state. You do any operation, any measurement on them, they will give you the same outcome. So I guess, for example, if you measure then in 0, 1 direction, do computational basis measurement, then what happens? Measure this ensemble, then 1/2 probability is 0, and it tells you 0. 1/2 probability is 1, it tells you 1. Then you measure those two things in computational basis. Well, 1/2 is plus, then that's 50/50 of tells you 0, 1. And 1/2 is minus, it's also 50/50 tells you 0 and 1. So those two ensembles give you the same same result of if you measure in computational basis is 50% 0 and 50% 1. And you can also see this thing and try to plug in this formula and see the probability is 1/2, 1/2. Okay, so it's surprising, but this is true. And we can have this more general. Yeah, so we have a theorem here. There is a unitary freedom of ensemble of quantum states. So any quantum state psi. And okay, so we actually start with a definition. Yeah. So any quantum state we can associate some pi. And so we define this subnormalized state psi tilde I. That's the square root of probability times your state. Okay. Then now two ensembles. So we actually start a theorem now. So two ensemble is pi psi and qj phi j. They represent I should say they have the same density matrix if and only if there exists a unitary U, such that now we use this notation. So those psi is basically a unitary rotation on those phi j tilde, okay. And therefore y. So there is this unitary U that transform those phi tilde to those psi tilde. And so for example, our totally mixed state has this one where the subnormalized state corresponding. Those subnormalized state tilde are 1 over square root of 0, 1 over square root of 1, and 1 over square root of plus, 1 over square root of minus. Then we can try to find this uij to write in this direction, right? So this is psi tilde 1, psi tilde 2 is phi tilde 1, phi tilde 2. Then 0 is 1 over square root plus 1 over square root 2 minus, and you remember it's 1 over square root 2 here, and then 1 is 1 over square root 2 plus minus 1 over square root 2 minus. So, and now you see this thing, this part is this, and this part is that. Also this part is this, and that part is that. So this 1 over square root 2 is your coefficient of u11, is u12, u21, u21. So your u is this matrix, and it's the Hilbert matrix. It is unitary. Okay, and then we have detailed proof, which we obviously don't have time to go over, and I'm not sure we want to go over it because it's a really annoying proof. So maybe I will leave this as a reading. Try to go through this. The proof, I can say the annoying part. So maybe we'll go over this really quickly. The proof is really annoying because you need to fix a lot of dimension. Most of the proof is setting up the notation so you can fix the dimension. Because here we have a nice example. So here we have a two-dimensional density matrix that correspond to two states, right? So what we didn't show is that the number of states here can be different from the dimension here. And the number of states here is totally arbitrary. You can have 100 different states mixtured and give you a 2 by 2 dimensional matrix. Okay? And yeah. And the number of states will correspond to the dimension of this uij here, right? Because this uij is sum over j is sum over number of example here. So this can be 100, and this can be also a different number. This can be 200. So I is the index from 1 to 100, and j is a number from 1 to 200. And uij is actually not a square matrix because I and j have different dimension, and you need to fill it up back to a square, and it's very annoying. Okay, so that's a complaint about the proof. But we'll see what we can do to skip all the annoying part and tell you the GSO proof next time. And yeah, so I guess we'll finish early today, and we'll finish our density matrix chapter next week. Any question? Otherwise we can stop early. Okay.